Hello and welcome to Algebra 1, Lesson 20. In this video, we're going to have an introduction to functions. So for most of you in Algebra 1, you've never seen or heard about functions before. I can tell you that it's a topic that does confuse a lot of students, but you really don't focus a lot on it in Algebra 1. You kind of briefly talk about it in your chapter on linear equations in two variables, and then in most cases, you won't see it again until Algebra 2. So if you don't get it here, don't be too worried. You're going to have a lot of opportunities in the future to kind of get really good at working with functions. All right, so let's start out with a basic scenario. So I want you to suppose you go to the store and it costs $2 per 1 ounce of granola. So this means for 2 ounces, the cost is $4, for 3, $6, and so on. To mathematically explain this relationship between the number of ounces of granola purchased and the cost, we could set up a little equation, right? We could set up a linear equation in two variables. So let's let y be equal to the total cost in dollars. And we're going to let x be equal to the number of ounces of granola that's purchased. So how would we take these two variables and set up an equation that describes our situation? Well, I know that 2, or $2 specifically, I'm going to leave off the dollar symbol. I know that 2 is the cost per ounce of granola. So this is the cost per ounce. And I know that x is representing the number of ounces of granola purchased. So if I multiply the two together, if I take 2, the cost per ounce, and I multiply by x, the number of ounces of granola purchased, that's going to give me the total cost, which is y. Right? This is the total cost in dollars. So there's an equation to represent the scenario that I just gave you. Now, the ordered pairs that satisfy this equation. So for example, one ordered pair would be 0, 0. If I plug in a 0 for x, meaning I don't buy any ounces of granola, I would get a 0 for y. I didn't buy any ounces of granola. I don't spend any money. Another one would be 1, 2. I buy 1 ounce of granola. I spend $2. Another one would be 2, 4. I buy 2 ounces of granola. I spend $4. Right? So on and so forth. So I can kind of put a comma here and 3 dots because this pattern would continue forever. After 2 for an x value, I would get 3, and I would just double it to get my answer. 3 times 2 is 6. Then 4 times 2 is 8. Then 5 times 2 is 10, so on and so forth. If I plugged in 27 for x, I just multiply it by 2 and get 54, my y value. One thing that you might not have noticed here is that there's a restriction on x. And a lot of times when we work with these real-world problems, you have restrictions. Why is there a restriction on x? Can you think about what x can't be equal to? Well, x specifically can't be negative. It can be 0 or it can be positive. So x is greater than or equal to 0 here, specifically because I can't walk into a grocery store and say, hey, I'd like to buy negative 18 ounces of granola, right? Maybe that's you selling granola or something like that, but we're not going to get into any complicated scenarios or thought processes like that. We're just going to say that, hey, we can only buy 0 ounces of granola or some positive amount. So there's a restriction here. There's a restriction. And we're going to talk a lot about this moving forward where we're limiting a variable to certain values. In this case, we're going to say, hey, it can only be 0 or some positive value. So the ordered pairs here that satisfy this equation have a special name when we're talking about functions. They're known as a relation. They're known as a relation. This is definitely a definition you want to write down. It's something you're going to talk about when you study functions. So a relation is just any set of ordered pairs. And we haven't really talked about what a set is either. We'll talk a lot about sets in Algebra 2. But for right now, just understand that a set is a collection of things. Okay? And when we work with sets, we put the elements of a set, and that's what's contained in a set, inside of what's known as set braces. So for example, here with these ordered pairs, I'll put them inside of set braces. Okay. So this would be the set of ordered pairs that satisfy this equation. And I can't possibly list all of the ordered pairs. So again, I have the 3 dots to say that the pattern here, where I increase x by 1 and y increases by 2, continues forever and ever and ever. Now, one thing I want to do really quickly is just graph this equation y equals 2x, where again, x is greater than or equal to 0. So I know the y-intercept occurs at 0, 0, right? It occurs at the origin. This is in slope-intercept form. I could put plus 0 behind this if I wanted to. Or you could just realize, again, that's a line that goes through the origin. Now, I can't have any points that correspond with an x value that's to the left of 0. So I'm only going to plot points up here because, again, x has to be greater than or equal to 0. So if I use my slope, I'd go up 2, I'd go up 1, 2, and over 1. Up 2 and over 1. Up 2 and over 1. So let's graph this guy. So this would be y equals 2x with x is greater than or equal to 0. Again, notice how we don't have anything down here like we normally would. And this shows the relationship between, again, the x-axis is telling us how many ounces of granola that we're purchasing. The y-axis is telling us how much it costs in dollars. So in other words, if I buy 1 ounce of granola, it's going to cost me $2. If I buy 5 ounces of granola, it's going to cost me $10, right? So on and so forth. All right, so let's talk a little bit more about some basic vocabulary. So we already know that a relation is any set of ordered pairs, and the ordered pairs are, again, x comma y. So in any ordered pair, x and y are known as the components of the ordered pair. Something that you want to write down because, again, when you start talking about functions, you get a lot of these new kind of definitions that are going to pop up. They might be put on your test. So just write down, again, in any ordered pair, x and y are known as the components of the ordered pair. Now, highly important here, the set or the list of all first components, so basically they're saying x values, in the ordered pairs of a relation is called the domain. You're going to hear a lot about the domain moving forward. What's the domain? Find the domain, right? So on and so forth. Now, the set or the list of all second components, again, these would be the y values, in the ordered pairs of a relation is called the range, okay? So you might get questions that say, what's the domain of this function? Well, you're looking for the set or the list of all possible x values. You might get a question that says, hey, what's the range of this function? Well, you're looking for, again, the list or the set of all possible y values. All right, so let's take a look at some basic examples right now. And we have more stuff to explain. We haven't even gotten to functions yet. But right now, we're just working with some relations, and we're getting down some basic vocabulary. So let's take a look at 2 examples. We have this set of ordered pairs. And again, when you have a set of ordered pairs, it makes up a relation. So the first ordered pair is 3, 7. The second one is 2, 1. The third one is -8, 4. And the fourth one is -2, 4. Now it says, what is the domain? So the domain, again, is the set of all first components. And again, that's kind of very textbooky, right? You want to say the set of all first components, meaning the set of all x's. So what are the x values in this relation? Well, it's everything that occurs first, right? These are your x values. That's all you're looking for if it asks you for the domain. So it's the number 3, it's the number 2, it's the number -8, and it's the number -2. So this is your domain. All right, so now we want to find the range. So we have this same relation, 3, 7, 2, 1, -8, 4, and -2, 4. So the range is the set of all second components or y values. So 7, 1, 4, and 4. So for the range, we'll have, and let me make that better, we'll have 7, we'll have 1, and we'll have 4. I don't need to list 4 twice. when you're writing a set, if you already have something in there, you don't need to list it again. So just 7, 1, and then 4. So let's take a look at another one. We have a relation here which is made up of these 4 ordered pairs. So we have -9, 3, 12, 7, -9, 4, and 1, 8. So what's the domain? Again, that's the set of all first components. So -9, 12, -9, and 1. So your domain, we've got -9, we've got 12, we don't list -9 again, and then we've got 1. All right, so now looking at the same relation, we want to know what's the range. So the range, again, is the set of all second components, so y values, so 3, 7, 4, and 8. So that's your range. And again, let me make that better. So 3, 7, 4, and 8. All right, so now that we've gotten some of the basic kind of vocabulary out of the way, let's start going a little deeper and talking about functions. So a function is a set of ordered pairs in which each first component, or again, that's the x value, corresponds to exactly one second component or y value. A lot of times you're going to hear for each x, there can be only one y. Now, in order to understand that, let's take a look at this relation here. So in this relation, we have the ordered pair 3, 2, 2, 1, 8, 4, and 9, 7. So in other words, this is going to be a function. And so not every relation is a function, but all functions are relations. You're going to hear that in your lecture from your teacher, or maybe your tutor will say it, or maybe you just hear me say it. But again, all functions are relations, but not all relations are functions. So if I look at each ordered pair here, this 3 corresponds to 2. So in other words, I have an x value that's 3. I have a y value that's 2. Here I have an x value of 2. It corresponds to a y value of 1. Here I have an x value of 8. It corresponds to a y value of 4. Here I have an x value of 9. It corresponds to a y value of 7. This is a function because for each x that I have, it corresponds to exactly one y value. Okay? And I know that doesn't really make a lot of sense when you first hear it or see it, but let me show you an example of something that's not a function. So maybe you'll see it that way. So this is an example of a relation that is not a function. So you've got a set of ordered pairs, but the problem is, okay, your ordered pairs, you have 7, -4, -1, 5, 7, 3, and 2, -8. So if you think about your x values, what do you have? You have 7, you have -1, you have 7 again. So remember, when we were listing our domain, we didn't list it twice. So I'm just going to keep that 1, 7 there, and then you have 2. So what are the y values? We have -4, you have 5, you have 3, and you have -8. So you can think about this as your x values, or again, your domain, right? Your list of first components. You think about this as your y values, or again, your range, your list of second components. Now for each x, there can be only one y, or there can be an association with one y. So 7 is corresponding to -4, but over here it corresponds to 3. That is a huge problem. Now -1 corresponds to 5, that's fine, and 2 corresponds to -8, that's fine. This is the problem right here, this 7. And when you have a function, you have to be able to say, okay, for this given x value, I know what the y value is going to be. So if I have an x value of 7, I need to have a clear association that I'm going to have a y value of this. And I don't here. I have two y values. I have a y value of -4 and I have a y value of 3. So there's no clear association between this x value and one y value. It's linked to two different ones, right? So that's a huge problem for us. So we're just going to say this is not a function. Not a function. And when you first start looking at problems in this section, these are the type of problems you're going to get. They're going to give you a relation, which is basically a set of ordered pairs. And they're going to say, is this a function? Is it not a function? And all you're basically going to do is look for duplicate x values. So if I see an x value here, that's 7, and another x value here, that's 7, and it's corresponding to two different y values, I don't have a function. So here's another example we can look at. We have this relation, again, just a set of ordered pairs. We have 7, negative 7, 2, negative 3, 6, 5, and negative 12, 8. So again, if you see this type of problem, all you're looking for is duplicate x values. I've got a 7, a 2, a 6, and a negative 12. Nothing's duplicated, so this is a function. Because for each x, there's one y. So every x I have, so in other words, if I said, okay, if I have an x value of 7, what's the y value? Well, it's negative 7. So if I have an x value of 7, I know that I get a y value of negative 7. If I have an x value of 2, I know I get a y value of negative 3. If I have an x value of 6, I know I get a y value of 5. If I have an x value of negative 12, I know I get a y value of 8. So this is a function. If I was to replace one of these, let's say this wasn't 6, let's say this was 2. So then in this case, it would not be a function. And why? Well, instead of 6 being linked to 5, I would have 2 that's linked to negative 3 and also 5. So in other words, if I said, what is the value of y given that x is 2, you really can't give me an answer. You'd have to say, well, it could be negative 3 or it could be 5. I really don't know. And the whole idea behind a function is that if I give you an x, you can give me a y. So if I say, okay, x is 2, you've got to be able to say, okay, y is negative 3, right? If I go back to the original example. If I give you an x of 6, y is 5. So in that case where I replaced this 6 with a 2, 2 was now linked to two different y values, and so it wouldn't be a function. But as it's originally written, as we have it here, where 7 is linked to or corresponds to negative 7, 2 is linked to or corresponds to negative 3, 6 is linked to or corresponds to 5, and negative 12 is linked to or corresponds to 8, we do have a function. All right, here's another example. So again, another relation, just a set of ordered pairs. We have negative 1, 3, 2, 5, 11, 7, and 2, 7. So right away, you should notice that you have duplicate x values. You have a 2 here and here. That's a problem because, again, if I list this out and I say, okay, my x values and my y values, so the domain, the set of x values that have negative 1, 2, and 11 only. For the range or the y values that have 3, 5, 7, and then 7 again. Negative 1 is linked to 3. 2 is linked to 5. 11 is linked to 7. But then 2 is also linked to 7. So that's where we have a problem. If I tell you what is the value of y given that x is 2, you don't know. You'd have to say, well, it could be 5 or it could be 7. There has to be a crystal clear association. So it has to be, I give you an x and you can give me a y. So again, this is not a function. All right, so here's another example. So we have a relation, again, a set of ordered pairs. We have 3, 5, we have negative 2, 5, we have 6, 8, and we have 1, 4. So some of you right away will make the mistake of saying, oh, I have a 5 here and a 5 here, not a function. You would be wrong. You only need to look for duplicate x values, okay? And I'm going to show you why that's the case in a second. But essentially, again, I have 3, negative 2, 6, and 1. No duplicate x values, so this is a function. And if you kind of list it out like we've been doing, so the x values are the domain. We have 3, we have negative 2, we have 6, and we have 1. And then the y values or the range, we have 5, we have 5 again, we have 8, and we have 4. Now, for each x, there can be one y. So for this x here, 3, it corresponds to 5. So if I say, hey, what is the value of y in this relation given that x is 3? You can answer 5, right? There's no other answer. If I say, what is the value of y if x is negative 2? Your answer is also 5, but that's okay. Two different x's can be linked to one y. No problem, because if you say, hey, what is the value of y given that x is negative 2? You have a clear answer. It's 5. That's all right. What you can't have, let me erase this real quick, we'll come back to it, is this going to two different ones. Let's say I had those two ordered pairs in there. Let's say I had something with negative 2, 5 and negative 2, 8. Well, that's an issue because I'd say, hey, what is the value of y given that x is negative 2? Well, it could be 5, but it also could be 8. There's no clear association between your x value of negative 2 and some y value. It's linked up to two different ones. So that's where we have a problem. So again, this is a function because for each x, we have one y. 3 corresponds to 5, negative 2 corresponds to 5, 6 corresponds to 8, and 1 corresponds to 4. So I want to kind of revisit one that we know is not a function already. And I want to draw a picture that's probably in your textbook. They'll probably set up something that looks like this. So your domain, this is your x values, right? Your set of x values. And we'll draw a little something that looks like this. And we'll list the numbers that are in the domain. So we have negative 1, we have 2, 11, and then 2 again. And then you'll see a picture with the range. So here's the range. These are the y values. And in the y values, or in the land of y, we have 3, we have 5, we have 7. So the problem, or the reason this isn't a function, we have negative 1 that's linked to 3. So if I leave from negative 1, I end up at 3. If I leave from 2, I end up at 5, but I also end up at 7. So there's no clear association there. And that's the big problem. I need to know that when I leave from 2, I'm going to end up at one location only. If I have a function, I need to have something where I say, okay, x is 2, y is some given value. Here x is 2, and y could be 5, or it could be 7. So again, there's no clear association. And then for 11, that's also linked to 7 over here. And here was an example that we did that was a function. So let's do the same picture. So we have our domain, or the x values. And let's draw a little picture for those. So we have 3, we have negative 2, we have 6, and we have 1. And then you have your range, or your set of y values. So you have 5, and that's duplicated, so I just put it once. You have 8, and you have 4. So again, for each x, there can be one y. So if I leave from 3, I know I'm going to 5. So there's a clear association. If I leave from negative 2, I know I'm going to 5. Again, it's okay that two different x's go to one single y. That's all right. Because in each case, I can say, okay, if I leave from negative 2, I know that I'm going to 5. If I leave from 3, I know I'm going to 5. If I leave from 6, I know I'm going to 8. If I leave from 1, I know I'm going to 4. It's only a problem when you leave from an x value and you go to multiple y values, because then there's no clear association. It's all about give you something for x, you've got to give me one and only one value for y. Okay, so there's much more to the topic of functions, but kind of in an Algebra 1 course, we're going to just kind of wrap up our lesson and look at something else known as the vertical line test. And then we'll kind of leave this topic until we get to Algebra 2, and then we'll get all into the land of functions. So the vertical line test. If any vertical line intersects the graph at more than one point, we do not have a function. So let's look at a graph and see why that's the case. So if I look at this coordinate plane, I just have some ordered pairs here. And I want you just to think about what the ordered pairs would be. So we have 3, 4 as an ordered pair. We have 2, 7 as an ordered pair. We have negative 2, 2 as an ordered pair. And we have negative 2, 7 as an ordered pair. And we also have negative 4, 4 as an ordered pair. So you can already tell just by looking at the ordered pairs that this wouldn't be a function, right? Because the x value of negative 2 occurs twice. But you can also determine this graphically by drawing a vertical line. So I'll go through and just make a vertical line really quick. If that vertical line hits the graph in more than one location, you don't have a function. Not a function. And why is that the case? Well, for each x value, okay, this x value is negative 2, it can only correspond to one y value. This x value of negative 2 corresponds to a y value of 2 and also corresponds to a y value of 7. So that's a problem for us. And if you don't have a function, you're going to have the scenario where a vertical line will cross at least two ordered pairs in your relation. So what about something like this, where we have the ordered pair -5, -2, -5, -2. We have the ordered pair -3, -3. We have the ordered pair -1, 4. We have the ordered pair 4, 1. And we have the ordered pair 6, -2. So for this relation here, we could see if we made vertical lines going down our coordinate plane, it would never hit in more than one location, meaning it would never cross more than one ordered pair. And the reason for that is we have a function. We have a function here. So let's say we came across the graph of a line. Would this be a function? We'll go through and draw some vertical lines and see if it intersects the graph at any place more than once. Well, it doesn't. Right? I can draw vertical lines all through this thing, and it's never going to hit more than once. That's because a line is a function. This is a function. What if I saw something like this? Would this be a function? Well, no, it's not. If I look at it, I can tell right away that for each x, I'm going to have more than one y. If I just draw a line through the x value of -4, I can see an impact here and also here. So this x value of -4 corresponds to two different y values. I can go through and make a bunch of different vertical lines. You're going to see it's going to hit the graph more than once everywhere. Right? So for each x here, there's more than one y. So this is not a function.